unique to the surface in question, and we have tabulated these coefficients for a variety of common surfaces, like glass, steel, wood, and rubber, and the various combinations thereof.
So notice the pattern. The higher the number, the more friction there is. You want tires that have very high static friction coefficients, which is the number here. If it's a low coefficient, that means the object will most likely slide easily.
As we said, once the applied force exceeds the maximum static friction, the object will begin to move. Bear in mind that this equation involves scalar quantities, not vectors, and therefore implies nothing about direction. As we said, static friction opposes the initiation of motion, but once an object is in motion, it is now moving against kinetic friction.
We might not learn kinetic friction this semester because we have so much to cover. We still have to get into circuits and magnetism and outer space. We have to get into space science. So static friction is what our physics problems can be focused on. But you can hear a little bit about it here.
This is the force that opposes relative sliding motion. Kinetic friction is always lesser than static friction, which you will notice if you try to push any object across the surface, like a heavy box across the floor. It will be more difficult to get the box going than it is to keep it moving once you've started. There are coefficients of kinetic friction as well, and these will be different from the coefficients of static friction for the same materials. These values allow us to calculate the magnitude of the kinetic frictional force acting on a sliding object. Friction isn't always a nuisance. It can also be used to our advantage. When we walk, the static friction between our feet and the ground allows us to propel ourselves forward, rather than our feet simply sliding back. Car tires take advantage of friction to move the car forward, and they are designed with grooves to divert water away so that it does not interfere with the contact between the tire and the ground. This allows it to maintain traction rather than skidding. We should note that air resistance is another type of fluid friction. When a car or a plane moves through the atmosphere, the particles in the air hinder its motion, offering some kinetic friction. This is true of motion through any fluid, in a way that depends on the viscosity of the fluid, which represents the fluid's resistance to flow. So by now we are familiar with a few of the vectors we will commonly use in physics. An object at rest on a flat surface on Earth will experience a downward force due to its weight, as well as an upward normal force that is equal in magnitude. If some horizontal force is applied, there will also be an opposing frictional force. If the applied force is less than the maximum static frictional force of that surface, the horizontal vectors will cancel each other out, just like the vertical ones, and the object will remain at rest. If the applied force exceeds the maximum friction, the object will accelerate in the direction of the push, and the kinetic frictional force will oppose its forward motion. So we can expect to see these four vectors in lots of the free-body diagrams from this point forward. A common example...
Okay, so we'll maybe discuss ramps later, but let's go ahead and solve our physics problem, so I can give you your practice problems, and then we can get into the study guide tomorrow, and then take your exam on Monday. All right, go to 03 centripetal force. Remember, force and acceleration are not the same thing. Acceleration is how something's speeding up or slowing down, and then force is how much push or pull there is that includes weight. The weight, and how fast that weight is speeding up or slowing down. Okay, the physics problem says, skidding on a curve. A 1,000-kilogram car rounds a curve on a flat road of a radius of 50 meters at a speed of 50 kilometers per hour. Now, what's most helpful is if you visualize this as this diagram here. You've got a car. It's going in a specific direction. It's trying to turn on a road. The car is 50 meters away from the middle of this imaginary circle that the road is part of. And the force needed to keep that car turning is centripetal force, or F sub C. So there's the car you have to imagine. Then you have to go even deeper in your imagination and think about the wheels of the car. The car's trying to stay on the track by turning and using centripetal force. but the wheels need frictional force to stay on the surface. So draw yourself a wheel after you've drawn. I'm going too fast. Let me have you first draw the car. Draw the car, the turn it's making on the track, and then label the track with your forces, your radius, and your speed. All of you are going to drive one day, and maybe you won't build a road for a city or a contract, but you'll understand what's happening. Not just with basic knowledge like, oh, my tires were, they were bald and they were running very low on treads. It's like, no, it's the frictional force was not high enough to keep the car from turning off the road, skidding off the road. And I do recommend you copy your screens because there's going to be a lot of calculations here that are hard to see. So use the front of the class as like a guide, but use your notes as what's on your screen. So the car is trying to stay on the road, and if you zoom in, the wheels are trying to stick to the road. So 4 forces are at work in the wheel. Gravity, we learned that last week. The normal force, we learned that last week. And then 2 new forces. Frictional force, which is from our video, and applied force from the video. The applied force is what the car is trying to do when it's moving really fast. It's trying to move in a straight line. Right? Newton's first law, objects in motion try to stay in motion. So cars try to drive in a straight line. But fortunately, tires can assist and generate a frictional force that keeps the car turning. So what we want to find is frictional force of the tire and compare it to the centripetal force of the car. I'll repeat that. We need to find the frictional force of the tire and make sure it's the same amount of force as the centripetal force. Otherwise, if it's too low, if our frictional force is too low, that means the car's going to slide right off a cliff, right into some trees, right into a building. And we all are going to drive one day and have that risk. So how do we find friction? How do we find centripetal force first? That's the first step. Well, you have to use your new triangle, which is in the warm-up. Find centripetal force to determine the minimum force needed to keep the car on the road. I'm going to add a little editing here. Needed to keep the car on the road. Maybe I shouldn't have done that, but I'll still see if I can scoot this over. I cannot. All right, forget the grammar. So, centripetal force equals mass times velocity squared over radius. But we don't have velocity given to us in the units we want. Right now it says kilometers per hour. So we're going to convert kilometers per hour into meters per second. Find V. Some students thought it was U in the warm-up. So I need to make sure my V's look different. The mass is 1,000 kilograms. The radius is 50. The velocity is 50 kilometers per hour. We need to change kilometers per hour into meters per second by multiplying it with a conversion factor, aka a fraction. If you multiply 50 kilometers per hour to 1,000 meters over a kilometer, you can cancel out the units. I'll do that now. Cancel, cancel. But we also want to cancel out the hours and get it into seconds. So you multiply that by another conversion factor, known as a fraction, and make it 1 hour over 3,600 seconds. Cancel out your hours. And what's left over is 50 times 1,000 divided by 3,600. Let me get a student to do this calculation. It's going to be from this class. Let's call on Kelvin. Grab a calculator. Put 50 times 1,000. Hit equals, and then divide by 3,600. Divide by 3,600 after that. .9. So your calculator is not in scientific notation? Okay, let's put it in there so we're all the same. So, good. That over. It will get annoying when you don't want scientific notation, and when you do want it, you switch back and forth. So this week, let's just stick to scientific notation. Try one more time, Kelvin. So go to the hundredths, 1.39, just like you did, but then multiply it by the exponent, which is E what? 1. And that is our velocity. Now we can plug our velocity into our force equation. Our force equation is not F equals ma. It's going to be force equals m times v. My v got erased. N times v squared. Let me see if I can get this to stick. Okay, m times v squared over r. Then we plug in 1,000, the mass, times 1.39, which is what Kelvin solved for us, 1.39 E1. Don't forget the square, divide by 50 meters. Let's choose a student to do the calculations. It's going to be Alexa. Grab a calculator and punch in 1,000 times 1.39 second x minus 1, 1, and then hit square immediately, and then click divide by 50. Do it all in one fell swoop, and you'll get what you need. So I'll repeat that. Put in 1,000 times 1.39 second x minus 1, 1, squared, divide by 50. What do you get? Correct. 3.86 E3. Now I'm putting N here for newtons because that's the units for force. You don't need to have that for your exam, but we will see the units of Newton later on this semester, probably in December. But newtons is how forces are measured. Meters per second is how velocities are measured. So what we found, class, is not if the car is going to skid off the road or not. What we found was how much force is necessary to keep the car on the track. Because the car is turning. How much force is needed? And that force should equal the amount of frictional force our tires are giving off as they grip the road. Frictional force needs to equal centripetal force. Or it could be more. If our tires are really good, brand new tires, and they really grip the road, the force will be greater than the centripetal force. It's guaranteed your car will stay on the road. So let's find out. We're going to calculate frictional force of our tires and see if it equals centripetal force. You need to use another new triangle, and that's probably why this is so challenging for students. We need to use a concept called the static friction coefficient. It's that number, the higher it is, the more friction there is. The lower the number, the less friction there is. Our practice problem says, if the pavement is dry, the coefficient of static friction is 0.6. If the pavement is icy, the coefficient of static friction is 0.25. Higher the number, more friction. Lower the number, less friction. So, if we wanted to find force of friction, it's going to be static friction coefficient times force normal. Sounds like a second language we're speaking. So let's set up our problem as that. Frictional force equals static friction coefficient times force normal. A lot of students ask me, what letter is that? And it's a Greek letter. It's called mu. Don't ask me how they got that. I mean, we have so many options on our keyboard, but they didn't have any options like we do back then when they invented it. So based on intellectual property and consensus, scientists have agreed we're going to keep this. It's like a lowercase m with a really long leg. Think of it like that. It's the mu. And that represents the static friction coefficient. Let's plug in. The static friction coefficient is 0.6, given to us in the problem. And our force normal is the opposite of force of gravity, which is negative m times g. Now, I'm not going to write that because I'm running out of room. I'm just going to write the negative mass times gravity. I mean, we could just look up here, and that's our formula, but this is just the exact numbers we want to put in our calculators. I'm going to call a student to do this calculation. It's going to be Michael. So grab a calculator and put 0.6 times negative 1,000 times negative 9.8. Tell me what you get. Say the whole thing. Did you get exponents on the right? So say it. Times 10 to the third, right? Otherwise known as 5.88 E3. So now we have, excuse me, the force the tires are giving off and how much force we need to stay on the road. Michael, if you compare these two numbers, which one's bigger? 5.88. The force of the tires, the friction, is higher than the force needed to stay on the road. So what do you think is going to happen to the car when it turns? Because if the force of the tires is lower than the force needed, the car flies off the road. So what's going to happen if the force is higher of the tires? Two options. Car stays on the road, car flies off. What do you think? The car will fly off. Is not it. Is inaccurate. The car will stay on. The car will stay on. The car will stay on because think of the tires as going two directions when your car is turning. There's the applied force and the frictional force. Every car wants to fly in a straight line, drive in a straight line. And that's why frictional force will keep the car on the road when the car's turning. As long as we have a higher frictional force than our centripetal force, then the car will stay on the track. Think of centripetal force as a string. Okay? If you take a yo-yo and you spin it around your head, if that string is strong, the yo-yo will stay on. If the string is weak, then the yo-yo will fly away from you in a straight line. Same thing with the car. You need a centripetal force number in your mind that the car needs to have in order to make the turn. If you don't have enough force, then your car can, if your car has too much force, then your car will just go off the road. So we compare the amount of frictional force being greater than our centripetal force to make that prediction. And now we're going to do the same type of calculation for an icy road. Use the same formula. frictional force equals the static friction coefficient times force normal. Plug in 0.25 this time, times 1,000, negative 1,000, times negative 9.8, and then multiply across. Next student calculating is Atsiri. Put in 0.25 times negative 1,000 times negative 9.8. Negative 9.8. Times 10 to the third. Will this car stay on the road when it's icy? What do you think? Why? Then the centripetal force. Centripetal force. Okay. All right, class. Let's see how